This is Unit 3, Video 10. In this video, we will talk about hybridization theory. That's a fancy word that will essentially describe how these orbitals become molecular orbitals. So it'll make a little more sense. So here it says it accounts for the geometry of molecules in terms of atomic orbitals. Now remember, atomic orbitals have a bunch of shapes. This is the s orbital. It has a spherical shape. There are 3 p orbitals, and 2 of them are shown here that have this 8 or dumbbell called shape. What will happen is we will take these 3 and hybridize them, mix them together, and create what are called hybrid orbitals, these purple ones. And these hybrid orbitals, you'll see, have a small lobe and the big lobe, kind of mixing the small s and the large p. And then these will come together and the whole molecule will be shaped like so. And we'll go through it step by step. Hopefully it'll make a little more sense. So here they are. These are the atomic orbitals, the s orbital, the 3p orbitals, and the 5d orbitals, if you recall. And the shapes of each. It's a good idea to understand the shapes, how the shapes of each of these look. And then we're going to look at how this is done. So consider CH4. Now CH4 will have a carbon in the middle and then 4 hydrogens on the outside. So if we were to draw its Lewis structure, it will look like this. Here's a bond as well. Now these are actually 4 equivalent bonds. Each of these bonds is exactly the same. In fact, they go to 4 opposite directions to minimize repulsion, and that's how we have a tetrahedral arrangement. So the question is, how can you get 4 equivalent bonds? Which orbitals? Atomic orbitals, the s, the p, which orbitals is the molecule using? Well, it has hybridized, it actually mixed an s and 3 p orbitals to form the 4 equivalent orbitals. So this is the orbital diagram of carbon. It actually has an s, one s that we're not going to, these are not the valence electrons, but its valence electrons are the 2s and the 2p electrons. So what will happen is it'll actually hybridize. Each of these boxes were represented with lines, so it has 4 orbitals in the highest shell, 4, you can say, valence orbitals, and these are the 4 that a carbon will actually hybridize or mix together. So here it takes the s orbital, the 3p orbitals, and then mixes them and creates 4 equivalent orbitals. Now we'll call these sp3 orbitals. So notice that each of these is designated as sp3 because you took an s and you took 3 p's and hybridized them, put them together, and that's how you get this structure right here. Again, this structure is tetrahedral, so all 4 of these have to go in opposite directions, and these are called sp3 hybrid orbitals. As you'll see, it'll be pretty easy to determine the hybridization, but here I want you to see how this works and why it works. Now if you have sp2 hybrid orbitals, an example of that would be if you have 3 areas of electrons. So what you'll need is you'll need to form 3 exactly the same orbitals. And to form 3 exactly the same, you'll need an s and 2p. So that's what happens. You get an s and 2p orbitals. This will be called sp2. Now you realize that there's 1 p orbital that's left that's not been hybridized. And that p orbital would actually be remaining unhybridized. It'll still look like the original p orbital, the one that has not been hybridized. So the 3 that have been hybridized then go in a plane. There's a plane which creates the trigonal planar arrangement, and they are all on the central atom. So hopefully this makes a little bit of sense. Here is a picture of what happens. So we took the s and the 2 p's, and together we hybridized into sp2 orbitals, and all 3 of them then will go in opposite direction. This is the first slide that we saw. Same idea. Now there is the unhybridized p orbital is actually still sitting here, and it's a little hard to see, but it goes above and below. It actually probably better to draw a big one here and a small one there to kind of show that it's coming out and in of the plane. And then finally, sp hybrid orbitals is if you only need 2 equivalent bonds, like in the case of CO2, here you only need 2 equivalent bonds. So all you'll need is an s and a p, and you would hybridize those to create 2 sp hybrid orbitals. And they will be 180 degrees apart because you have linear arrangement. And here then you have 2 unhybridized p orbitals. In fact, what happens is you have 2 p's that have not been used, and those 2 p's are still sitting here, and we'll show you what this picture looks like. Now, the d orbitals also come into play, and anytime you have expanded octets, since you've used 3 p orbitals, say if you have to have 5 electron areas, well, that gives you an s and 3 p's. Well, you need one more, or actually, in this case, yeah, you need one more, and so you'll need to dip into the d orbitals. So you can actually talk about sp3d and sp3d2 hybridization. So for trigonal bipyramidal, where you need 5, you'll talk about sp3d. For octahedral, when you need 6, you'll have to pull in 2 d orbitals for the hybridization. Now, in order to do this is actually pretty simple. And to assign hybridization, you'll draw a Lewis structure, as we've always done, and then count the electron domains. These orbitals, just like the bond angles that we saw before, will be based on electron domains, not molecular domains. And then the number of electron domains you have will be the number of orbitals that you will need to hybridize. And then you'll name it as sp, sp2, sp3, and so on and so forth. So, very simply, if you have a linear arrangement, you just need 2. Linear gives you 2 electron domains, so just the sp2, or rather sp. Trigonal planar has 3 electron domains, so you need sp2. Tetrahedral 4, that's why you need 4 orbitals. Trigonal bipyramidal 5, and on it goes, and that's how it works. Octahedral has 6, and that's why you would need 6 orbitals, an s, 3p, and 2d for a total of 6 orbitals that have to be hybridized. And that's really how it works. Let's go and do some examples. So, to indicate the hybridization, we'll have to draw the molecule as we've done before. NH2 minus is actually a polyatomic ion, but you got yourself a nitrogen in the middle, 2 hydrogens on the outside, and this is the structure that you have. Now, what you've got to consider when you're hybridizing is you have to consider all the electron domains. So in this case, you have 4 electron domains, 1, 2, 3, 4. So we have to make 4 equivalent orbitals. We'll need to use an s, and we need to use the 3p for a total of sp3. And that's actually our answer. It's actually pretty simple as that. Let's do SF4. Now be careful, SF4 could have expanded octets. So you have 6 coming from sulfur. You have 7 times 4. You have a total of 34, not 32, but 34 electrons, because this gives you 28. So you have 34 electrons. So with 34 electrons, you do have an expanded octet. So don't assume just because you have 4 atoms on the outside that it will be tetrahedral. In fact, in this case, after you draw the molecule, every fluorine should be fully octet. And that gives you 32. You need an extra pair of electrons on the sulfur. Now, this gives you 5 electron domains that you must consider. So 1, 2, 3, 4, and 5. These go as far as they can from each other to create the shape. In this case, the shape would be seesaw. But what you realize is that the 5 will require you to use 5 orbitals. So you need to use an s, a 3p, and you'll need to dip into the d. This gets you sp3d hybrid orbitals. And finally, CO is going to be pretty simple, but I wanted to show you what a simple molecule looks like. In this case of CO, you've drawn this one before. This has a triple bond between the carbon and the oxygen. Now, here you can consider 2 central atoms. You can either think about carbon or oxygen, and you will actually get equivalent hybridizations. But technically, you would need to assign a hybridization to each of the central atoms. So for carbon here, you have 2 electron domains, 1 on this side, 1 on this side. So all you need is S and P, so carbon is sp hybridized. Oxygen turns out to be exactly the same. You have 2 orbitals, so oxygen is also sp hybridized. Now with an sp hybrid orbital, what you've got, let me show you this, is you have on the oxygen and on the carbon unhybridized p orbitals. So actually you have 2 p orbitals here on the carbon. And since, remember, you have s and 3 p's available, we've used these 2 up, but 2 p's that haven't been used are actually still sitting there. So on the carbon, there's actually one going above, one going below, and then the other one, you can say, comes in and out of the board, like this. Same thing with oxygen, there's one above, one below, one in, one out. And that's a bit confusing, but it turns out, as you'll see, that these p orbitals can actually come together and can actually interact with one another. And what you'll get is you'll get a special type of bond. And that special type of bond is not here. So we will have to do an extra example. So let me actually show you. What happens is the extra bond that you get here between the P that have not been hybridized is called a pi bond. This guy here is called a pi bond. And since you have two pi bonds, since you have two of these unhybridized p orbitals, you also have a pi bond between these two. So this is also called a pi bond. Now, the bond that was between the two, so in fact, this one right here, the middle one, represents just the bond between the two atoms. But the second one and the third one, the double and the triple bond, actually represents this pi bond, and this one represents this pi bond. It's a little messy, but what you've got is you get two pi bonds. The double and the triple is called a pi bond. And then the one that's in the middle, that's technically a single, is called a sigma bond. This one right here is actually called a sigma bond. This is actually an S from the Greek alphabet, so this is called a sigma bond. And these out here are called pi bonds. Just like the pie that you eat, or that you celebrate with your math friends. Okay, so if you go back, what you have here on this molecule, you actually have two sigma bonds. What you have on this molecule is you have four sigma bonds, because you have four single bonds. And then this molecule here, this CO molecule, actually has two pi bonds and one sigma bond. I guess we can show you an example in class that combines these sigma and pi bonds. So also know about the sigma and the pi bonds in case we ask. All right, this should wrap up video 10 for us of the unit.